It was American author Ralph Waldo Emerson who said, "Build a better mousetrap and the world will be the path to your door." In this lesson, we're going to describe how to choose sample subjects without bias. We're going to use random number tables. We're going to explain methods used to reduce bias in experiments, and we're going to create diagrams for experimental design. All to answer the question, innovations, inventions, and investment. Where do ideas for new products come from? Before we get into it, let's take a look at warm-up number 2. Find the mean, median, and mode for the following set of airfares. Round to the nearest cent. So if we start off with the easiest ones, like the median, what is in the middle? And we can track our way back and find that the middle is $455. So the median is $455. Now the mode is the most common. And as it turns out, there is none. There is no mode for this because there's no repeated value. Now, when it comes to median, we have to add up all of these values. And when we add them all up, we get 3,310.02. But we need to divide this by 7, which is the number of entries. And that's going to give us $472.86 as the mean. Now, let's take a look at a problem that you will be able to do by the end of this lesson. Skippy's manufactures skateboard wheels for professionals. Skateboard wheels are prone to flat spots, which make them ride poorly, so they have to be replaced. The life of their Circle Master wheel is normally distributed with a mean of 5.8 months and a standard deviation of 1.1 months. An engineer at Skippy's has been tinkering with an improvement to the Circle Master wheel. He manufactures 100 of them to test and finds that the mean life of 8.8 months. Do you think this is enough evidence the new wheel will last longer? The distribution of the old style wheel life should be plotted and labeled. The mean is shown along with the plus or minus 1, plus or minus 2, and plus or minus 3 standard deviations. If you need a reminder, you should take a look back in the first unit where the lesson was vacation expenses to refresh your memory on using normal curves. A new improved wheel sample had a mean life of 8.8. So we're going to plot this on a normal curve, which means we need to convert 8.8 to a z-score. Remember, z is equal to x minus mu over the standard deviation. This is going to give us 8.8 minus 5.8 divided by 1.1, which is approximately 2.73. Now we're going to go to the normal curve table, the z-score table that we used back in that lesson, to find the z-score of 2.73. And the shared area is 0.9968. Since the area under the curve is 1, the area to the right of 8.8 can be found by subtracting that from 1, giving us 0.0032. There is a 0.32% chance, or about 1/3% chance of one randomly selected wheel lasting 8.8 months if it is an old style wheel. The engineer got an entire sample to average out to 8.8, which is an even more improbable occurrence. If the new wheels are not superior, the company has two choices of what they can believe based on the results of the study. First, they can assume the new wheel is not superior and that the sample was just by chance a batch of old wheels that lasted much longer than usual. Or 2, the new wheel are in fact superior. The company would really have to pick choice 2 because the chance of choice 1 occurring is very, very small. This type of logic is part of the hypothesis testing, a field of statistics that focuses on experimental and observational studies. Even before the Industrial Revolution of the 1800s, people had creative ideas that made a task able to be done better, more efficiently, and more quickly. Many of these inventions are still with us today. Thousands of years ago, people used logs as wheels to move heavy stones. They chipped away at rocks to make sharp implements, the first knives. As a member of today's technological world, many of these inventions you see are more sophisticated and more technological. New apps, computer hardware, phones, video and audio components, and so on. But take a look around you and ponder the impact of inventions we take for granted, whether they're physically simple or complicated. Things like zippers, airbags, transparent tape, eyeglasses, the ballpoint pen, adhesive bandages, marshmallows, elevators, air conditioning, tires, cornflakes, paper, cameras, compact discs, trampolines, mirrors, pencils, Formica, the Zamboni, lip balm, and plastic. You could easily make a list 10 times longer on your own. It is often said that invention is the mother of necessity. If there is a problem, often there is an inventor looking to solve it. Think of the plastic white spacer that keeps the cardboard pizza box from sticking to the cheese of the pizza pie. How many millions of them are sold each year? Think about the child-proof cap for aspirin bottles. How many millions are sold each year? An invention does not have to be intricate or electronic to be useful. Usually, inventors file a patent with the government claiming ownership of the idea for the invention. This gives the inventor certain rights. When inventors mass produce their invention, they apply for a trademark. A trademark is a recognizable logo, font, artistic design, or specific phrase associated with a particular product or service. New ideas from inventors find their way into the market through investors and corporations every day. New inventions can make inventors and corporations rich. How do inventors know if the product actually performs as intended? How do inventors decide what inventions will be accepted by the public? In this lesson, you're going to learn about statistical techniques that help answer these questions. Surveys are one way which inventors can get the opinion on a new product. When someone takes a survey, they should not be able to read into the intention of the preferences of the survey. When there is an unfair influence on the results, this is called bias. Questions on surveys must be worded in an impartial way so that they don't lead the reader to a certain conclusion. Leading the reader is known as question word bias. The interpretation of a question's meaning depends on the specific words chosen, and all people taking the survey should ideally interpret the question the same way. Imagine these two questions given the taxpayer on raising taxes to build a flood wall in a waterfront community. Are you in favor of building a flood wall that'll cost taxpayers $17 million? Or are you in favor of building a flood wall that will save many homes and make our community safer in the case of flood? Do you see how these questions lead on the reader? They are both examples of question word bias. All corporations must avoid question word bias when they need the feedback on a new product. Now let's describe how to choose sample subjects without bias. The Bloopy Balloon Corporation is interested in how the public feels about the new product they're developing for children's birthday parties. They need to show the product to a group of parents of young children and have them fill out a questionnaire. Bloopy's survey asks if the person is satisfied, dissatisfied, very dissatisfied with the new product. Is this an example of question word bias? On Bloopy's survey, each question has only 3 possible answers. Notice that 2 choices depict negative reaction, and only 1 choice is positive. This is one example of question word bias. Now let's check your understanding. A corporation has 10 questions. Which of the 5 possible responses, very satisfied, satisfied, no opinion, dissatisfied, very dissatisfied, are the responses an example of question word bias? And explain. The responses do not seem to have any bias since there are 2 satisfied, 2 dissatisfied, and 1 neutral response. However, it is possible the questions themselves could be biased. Now, let's use a random number table. The Bloopy Balloon Corporation needs a sample of young parents to show the new product to. How can Bloopy select the participants to maximize the chance they have a representative sample of the population? Bloopy needs to try and make sure their sample has as little bias as possible. The best way to ensure this is to select the participants randomly. Can you imagine how a sample of people all from the same profession, income level, neighborhood, and so on might influence the results? They decided to include 40 participants. The corporation needs to pick the participants randomly from a population they have reasonable access to. They are not going to pay airfares and hotel costs to fly in random participants from all over the country. They need to get a list of 977 participants in the 4 local elementary schools. They number the parents from 1 to 977. They use a random number table as shown to randomly select the parents that will participate in the survey. The random number table is a list of digits that were randomly generated as if someone pulled a marble numbered 0 through 9 with replacement repeatedly. They start on randomly selecting line 11 on the random number table, and the box 3-digit numbers are 977 or less. So we're going to get 669, 574, 463, and keep selecting in threes. Now at the end of this we get a 2-digit number, and we will simply combine that with the first number on line 12 and keep selecting numbers in group of 3. The parents chosen for the survey are numbered 669, 574, 463, 206, 089, 136, 180, and so on. Notice that 180 box required moving to line 12 to complete the 3-digit number. Also notice that 978 will be skipped because there is no parent number 978. The procedure continues until 40 participants are chosen. The use of random numbers helps ensure that no bias took place when choosing the participants. Let's check our understanding. The long-lasting light company designed a new type of bulb. They're testing it for defects. They need to pick 60 bulbs from the first lot of 500 bulbs to see if the bulb lasts 2,000 hours as they claim. If they number the bulbs 1 to 500 and start at line 3 on the random number table, what are the numbers of the first 5 bulbs that will be tested? So we start on line 3. We're going to take 899 and eliminate it because it is too high. So 343, 506 gets eliminated, it is too high. 391, 182, 692 gets eliminated for being too high, and 098. Then eliminating 907 for being too high and choosing 299. Now let's explain methods used to reduce bias in experiments. Using a random number table to avoid bias in sampling. So to test new products, corporations need to conduct an experiment or experimental study. In an experiment, one of the variables is deliberately manipulated to see if it has an effect. Take a look at the check your understanding problem from example 2. The new bulb has a different material composition than the old bulb. The corporation wants to set up an unbiased experiment to compare 2 types of bulbs. They need a sample of the old bulb and a sample of the new bulb. They can use a random number table to pick the samples from a large lot of each type of bulb. This is called randomization. They decide to test 50 of each type of bulb. This is called replication. They repeat the experiment on many bulbs rather than just using one bulb to make their conclusion. The one bulb which are used for comparisons form the control group. The new bulbs that are being experimented with form the experimental group. The experimental group is the group in which the changes are made. The 2 groups can be compared. Now let's create diagrams for an experimental design. The long-lasting light company wants to run a test to compare the length of life on their new bulb compared to their old bulb. They want to make sure the test is not biased. How can they design a fair test? The company can create a completely randomized design. In a completely randomized design, bulbs from each group would be randomly selected using the random number table. The project engineer constructs this diagram currently on the screen. The control group is used to see if the changes make any difference in the experimental group. The control group provides a benchmark for comparison. A large sample size, randomization, and completely randomized design, manipulation of variables, and control group all help ensure a long-lasting corporation that they have designed an unbiased and valid experiment. Let's check your understanding. If the Long Last Corporation runs their test and finds an average bulb life of 2,007 hours on the new bulb, does that mean the bulbs tested lasted longer than 2,000 hours? Explain. No, unfortunately, some of the bulbs could have lasted less than 2,000 hours. Let's extend your understanding here. A candy company is testing market reaction to a new flavor. Explain why they should not select their sample by looking for people in the parking lot of a health food store. Well, that sample would likely be biased against the consumption of candy. The Fierstein Tire Company needs to test a new type of tire they claim will last 20,000 miles longer than their old tire. They need to test the tires before the company can make this claim. The project manager does not want to use a completely randomized design. He is afraid the random sample of drivers who receive the old tires will have different cars, driving habits, and drive on different road conditions than drivers who receive the new tires. What kind of design can he set up to minimize the effect of different driving variables in the sample? Fierstein should set up a matched pair design to reduce the influence of the individual drivers. In a matched pair design, pairs of subjects are matched to eliminate individual differences. In this case, Fierstein can give 2 old-style tires and 2 new-style tires to each driver randomly selected to participate. Then, the difference in wear of the tires cannot be influenced by the different driving conditions since each driver had new and old tires. Let's check our understanding. The Mikey Sneaker Company has improved their sneaker laces. They want to see if the new laces are more durable than the old one. Explain what type of design they should use and why. They can use a matched pair design and have one person use both types of laces, one on each foot. Then all other variables are controlled for since the sneakers are on the same person. Beep's Jeep Showroom is looking to run a contest, and they need to pick the prizes. They are doing a study to determine if people who vacation in the United States are more likely to drive Jeeps than people who vacation outside the United States. How can they design the study? Here, what type of car and where they vacation have already been determined. The researchers just want to find out the existing information to help them make decisions. Unlike the light bulb example, the researchers have no ability to change this pre-existing information. As a result, this is not an experiment. This study is an example of an observational study. In an observational study, the researchers have no ability to alter the comparisons. They need to randomly select subjects and give them questionnaires. This observational study can be designed using a completely randomized design. Beep's Jeep Showroom can do an observational study using a completely randomized design. Let's check your understanding. A driving school wants to compare the number of accidents its graduates were involved in the 2-year period since they finished a defensive driving course. They want to compare men to women. This is an example of an experiment study or an observational study. Explain. It is observational. They're simply collecting already existing information to analyze and compare. Corporations always want to improve their product. They frequently run experimental studies to see if the improvements do what they're intended to do. Although inventors and factory engineers have theories as to how and why they suggest different improvements, their theories are only a hypothesis. A hypothesis is an educated guess or a reasonable explanation based on evidence and/or experience. A hypothesis test is used by statisticians to determine if there is evidence to believe the hypothesis. The next example helps you understand the logic of hypothesis testing. Skippy's manufactures skateboard wheels for professionals. Skateboard wheels are prone to flat spots, which make them ride poorly, so they have to be replaced. The life of their Circle Master wheel is normally distributed with a mean of 5.8 months and a standard deviation of 1.1 months. An engineer at Skippy's has been tinkering with an improvement to the Circle Master wheel. He manufactures 100 of them to test and finds that the mean life of 8.8 months. Do you think this is enough evidence the new wheel will last longer? The distribution of the old style wheel life should be plotted and labeled. The mean is shown along with the plus or minus 1, plus or minus 2, and plus or minus 3 standard deviations. If you need a reminder, you should take a look back in the first unit where the lesson was vacation expenses to refresh your memory on using normal curves. A new improved wheel sample had a mean life of 8.8. So we're going to plot this on a normal curve, which means we need to convert 8.8 to a z-score. Remember, z is equal to x minus mu over the standard deviation. This is going to give us 8.8 minus 5.8 divided by 1.1, which is approximately 2.73. Now we're going to go to the normal curve table, the z-score table that we used back in that lesson, to find the z-score of 2.73. And the shared area is 0.9968. Since the area under the curve is 1, the area to the right of 8.8 can be found by subtracting that from 1, giving us 0.0032. There is a 0.32% chance, or about 1/3 of a percent chance of one randomly selected wheel lasting 8.8 months if it is an old style wheel. The engineer got an entire sample to average out to 8.8, which is an even more improbable occurrence. If the new wheels are not superior, the company has two choices of what they can believe based on the results of the study. First, they can assume the new wheel is not superior and that the sample was just by chance a batch of old wheels that lasted much longer than usual. Or, two, the new wheel are in fact superior. The company would really have to pick choice 2 because the chance of choice 1 occurring is very, very small. This type of logic is part of the hypothesis testing, a field of statistics that focuses on experimental and observational studies. Let's check our understanding. If the 100 sample new wheels from that example had a mean life of 5.82 months, would you have believed the new wheels were superior, and explain? Since 5.82 is so close to the original mean of 5.8, the sample mean of 5.82 might have occurred due to chance. This result would not convince us that the new wheels are superior.